Hello, and welcome back. Today, I'm going to make a little toy. A toy for my children to play with that demonstrates a principle of mechanical engineering known as the mechanical paradox. To build this, I'm going to have to use a few different tools. I got the idea from a YouTube channel called TheDadLab. It's a great channel that has fun ideas for experiments that you can do with kids. And I particularly like this one because of the surprise that it causes when you do it correctly. So, the experiment with the toy consists of a few basic items. First, we have a setup of a couple of rails. And these rails do not run parallel to each other. And they do not run parallel to the ground. In fact, they are on an incline. So if we were to look at this from the side, it would look something like this. And if we were to look at it from the top, it would look something like this. So, what we use is a couple of objects to roll on these runners. In the first instance, we place a cylinder on the runner, and as expected, the cylinder travels down the incline. The interesting part of these experiments is not when we use a cylinder, but when we compare it to another object, namely an object called a bicone. A bicone. Now, a bicone is simply a cone which has been placed on top of another cone. It's that simple. So if we imagine the bicone in place here, it would look something like this. And over here we could imagine it to look that. And up here, it would probably look something like that. Now the question is, what happens when you place the bicone on the rails? And we'll come to that later. For the time being, though, let's get to 3D modeling, and we'll build a very simple cone and a very simple cylinder. And we'll print these off with a 3D printer. Now, for the cone, we'll have to print it in two parts and then stick them together. The reason for this is that we want to actually print a cone that has quite a wide angle. And if we try to do that with a 3D printer, and this angle is less than 45 degrees, then the print will most likely fail unless we use support struts. And the support struts will create a slightly uneven surface on the print area, and that will potentially ruin our experiment. So we'll print it in two pieces. The reason why you can't really print less than a 45-degree angle in this way is interesting in and of itself. If we imagine the cross-section of filaments butting up against each other in a print surface, if you imagine these are lines of plastic that have been deposited by a print head, if you then want to, on the next layer, print an overhang, you need a minimum adherent surface of half of the previous layer. Like that, you can create an overhang that is 45 degrees. If you attempt to print further out, the contact area is so small that the filament will likely not stick, and the print will fall apart, and the whole thing will fail in a mess of PLA noodles. So we'll move this into the virtual space now and make a couple of models on the computer. The first thing I'm going to do is, using Fusion 360, make a little sketch of a right-angled triangle. We're going to make the sketch on the XZ plane. That'll simplify 3D printing later. So we'll just start by sketching out a very basic shape here. You can here we now have a simple right-angled triangle. What we'll do now is we'll define some dimensions. We select this side, and our build volume is somewhere in the region of 20 centimeters. As we're actually going to rotate this shape around, we only want this side to be about 10 centimeters. So we'll put in 100 millimeters. We'll also want to define the height of our cone. That will be using this axis here. Now 40 centimeters actually seems like a pretty reasonable size to me. We can always come back and modify that later. So let's just stick to 40 for the time being. Okay, so our basic sketch is complete. So we now want to create an object using a revolve. The revolve basically selects a two-dimensional shape and revolves it around an axis to create a three-dimensional shape. So we'll select our triangle, and we'll select this axis, the height of the cylinder, to revolve it around. And we'll do a full revolution. That just means that we're going to do a 360-degree revolution around the axis to create one continuous shape. And if I change our angle of view, you'll be able to see we've created a cone. Now, it is a very squashed cone, and that is by design. We want this cone to have a very large width, but not too much height. And when we print this off, we'll stick another cone to the bottom. We'll print 2 copies, and that will make the bicone that I'm after. The next thing I want to build is a cylinder. This is very simple indeed. Before we start, let's save this one. And we can export this cone as an STL file for later printing. And you can see here, it's automatically opened it in the slicer so that we can print it off. But we'll put that to one side and carry on making our cone. Now, let's create a new design. And here we're going to make a sketch. And this time we're going to make the sketch on the XY axis. Again, this will facilitate printing. And this will be very, very simple indeed. What we'll do we will draw a circle. And we'll make that circle, I think 50 millimeters is good. It's more than enough. The radius of the circle is not so important. What's more important is the height of the cylinder. So, to create that height, we're simply going to extrude the circle we have made. And we'll extrude it out in the Z direction. Now, the cone we made before was 4 centimeters high. And because it'll be a bicone, that'll actually make it 8 centimeters high. So we'd want our cone to be about 8 centimeters tall as well. And there we have our cylinder. Once again, we can extract that and save it as an STL. An STL file is simply a representation of a parametric model in triangles. So this file here is describing this cone entirely in triangles, and you can see from these small ridges on the surface of the cone that it has in fact been turned in from a mathematical model into a representation using discrete quantums. This object here is actually a wipe tower. It's not something we need to worry about, as that will get moved away. It'll disappear once we send the object to the printer, as we're not printing in multiple filaments. Okay. Let's put this away and get the print started. And once the print is started, I'll assemble the pieces. And I'll show you how this little toy works. I quite enjoyed the way that it confuses children who have certain expectations of how things should work. And in fact, it's quite confusing for adults too until you understand the physical principles at work. So, I'll be back momentarily to reassemble the printed parts. Here we have the printed parts. I was able to capture a time lapse of the cylinder being printed, but not the cones. The cones were 7-hour prints, which would have been too long. I did attempt to get a time lapse, but it failed on a couple of occasions. See this lovely textured base. This is thanks to a new print bed that I have installed on my printer, which is powder coated. Gives it this lovely texture, and it improves the adherence of the first layer during the print. Nevertheless, we have a small defect here, where the filament has become slightly unstuck during the first few layers of print, but it hasn't affected the overall print. That seems just fine. If you look closely, you can see all the layers. The printer's building up the three-dimensional model right up to the tip, where you can see it's just a tiny little circle. And if we look at this through the light, you can actually see the lattice of structure inside the part. It's very faint, but you can just about see it. These little square shapes. Because it's not a solid piece of plastic, it's built with little compartments, little cells, to save on plastic and to make it lighter. Now our cylinder doesn't require any further manipulation, so I'm going to put that to one side. For the cones, however, we do need to glue them together. So I'm going to get my trusty glue and I'm going to glue these pieces together. This is the finished product. You can see it's the bicone that we were after. I might decorate it a little bit just to give a better sensation of the rotation as it's happening. We'll now build the rail rig. I'll be back soon with the assembled rig so we can have a look at how it works. Here we have the finished product. I took a few steel tubes and welded them together to make this track. These round tubes run from a wide end to a narrow end, and they drop a total of 8 centimeters over the course of the track. For the legs and the ends I use square tubing. what's holding this together are quite frankly awful. And that's because this is the first time I've done pretty much any kind of welding. Welding is a lot harder than it looks. Nevertheless, welds are holding and the track has worked. It's not beautiful, but it's functional. The cylinder we printed earlier, I have wrapped elegantly with a little sheet of toilet paper. The reason for this is because it's quite noisy when it rolls on the track, and this is a bit of a silencer. So, the principle we're looking at is the mechanical paradox. So I'm going to start by showing you the behavior of the cylinder. The cylinder behaves in a very, very natural, expected way. If we place it at the top of the incline, it quite reasonably rolls downhill. We can do that again. There's nothing particularly exciting or strange about that. If we take the bicone and we place it at the top of our track, it doesn't actually do anything. Let's try and give it a little push. Seems to want to go back. Let's try it at the bottom of the track instead and see what happens. It appears the bicone actually wants to roll uphill. Let's do that one more time. This is the exciting and strange behavior that I was talking about earlier. And the explanation for it is actually quite simple. This experiment demonstrates the concept of a center of mass, or a center of gravity. The bicone center of mass is here between these 2 points, in the middle of the object. The cylinder's center of gravity is in the center of the 2 circular faces, in the middle of the object as well. In the case of the cylinder, as it sits on top of the tracks, as it rolls downhill, its center of gravity rolls downhill. In the case of the bicone, for it to roll down the track, certainly can't do that. The center of gravity of the object is in effect the point at which gravity appears to pull it down. So when you look at it carefully, you'll see that although the whole object appears to be rolling uphill, its center of gravity is going downhill, thanks to the fact that the track is wider at the top. And so the cone appears to roll uphill. I have a couple of little frayed edges here. This is because I dropped this a few times as I was testing my track, getting it just right. I'm going to pack this up now so that I can take it to my kids' school and do a little demonstration for them. I hope they'll enjoy it. I hope I've managed to bring you a little bit of relaxation and maybe even a little bit of sleep. I hope to see you again sometime in the future here on my channel. See you soon.